So before we continue on with what you think of as normal organic chemistry, let's discuss a little bit the physical properties of some organic compounds, because it follows on quite nicely as a further illustration to what we were talking about last week in terms of intermolecular forces. So anyway, here are our first 10 alkanes. Okay, their state at room temperature, well, gases for the first 4, although for propane and butane, where we say they're liquefiable gases, that means that we can put a bit of pressure on them, turn them into liquids. We cannot pressurize methane and ethane in a reasonable way to turn them into liquids. But then after butane, remaining are liquids. And that is, of course, because their melting points and boiling points are generally increasing as they get bigger, because all we have in the alkanes are dispersion forces, and with dispersion forces, melting point and boiling point increase with mass. It's a little bit of a flip here with propane. I don't actually understand why propane has got a lower melting point than ethane, whereas it should of course be between ethane and butane. But what the heck, there are things we just don't know. At least I don't know. If anyone wants to look it up and come up with a decent reason for it, let me know and I'll give you some chocolate. Anyway, when we plot these out, nice little almost linear increase in the melting point, almost a linear increase in the boiling point as we increase the number of carbons. And of course, remember, in an alkane, every carbon increase also has 2 hydrogens going along with it. And there's that little acetone blip there. Continuing on, look at the density. Obviously, your gases, which are in grams per litre here, much less dense than the liquids, which are in grams per cubic centimetre. Do notice, however, that all of these alkanes have a density significantly less than water, so they do float on water. And Joel has a lovely little pun that I'm going to say now and ruin it for them, that alkanes are like witches, they float on water and they burn, which has a lovely tie-in to Monty Python and the Holy Grail, which is a movie that I strongly suggest that you watch. Something that I think is cute that we should spend more time on, but we don't, is that as molecules can't pack as closely together, there is an effect on the melting point and the boiling point, as you might expect, in terms of the fact that we've got to break those London dispersion forces in order to melt or to boil a species. And the closer the molecules can get to each other, the stronger the London dispersion forces. Thus, for example, if we have a look at this little series of octanes, the straight chain boils at 126. You put on a 2-methyl group there, so now it can't quite pack as closely together. You reduce the boiling point a smidge, put on a second one, you reduce the boiling point even more, and then throw on a third one, so they really can't pack well together, and you reduce the boiling point even more. So linear molecules pack together well because you've got surface contact, that increased London dispersion interaction. Branch molecules, not so much. Now let's move off of our hydrocarbons and start thinking about a few functional groups, just to see what effect different functional groups have upon these physical properties. In particular, we're going to be looking, of course, at the boiling points. Start off with the halogenoalkanes, in which we look at the electronegativity values. Carbon's actually a relatively electronegative atom. A lot of times people don't think about it that much, but it's pretty electronegative, but of course not nearly as electronegative as fluorine, chlorine, bromine, and a little bit less electronegative even than iodine. That means that when you introduce a halogen into an alkane molecule, you're introducing a polar bond, which will therefore affect the physical properties. If we just look at the boiling points, there is good old methane, minus 162, introduce the fluorine, so now we've got the dipole-dipole moment in there, and we're up to minus 78. Make it a little bit bigger, less polar, but bigger as you go from fluorine to chlorine. Do notice that having polarity is important than not having polarity, but if you've got 2 polar molecules, the heavier it is, the more likely it is that it's got the higher boiling point. So as we go to the heavier halogens, we're increasing the boiling points there. And again, just to emphasize, methane, dispersion only, dipole-dipole, and dispersion once you've got those halogenoalkanes. Moving to alcohols. There's the formula. What do we have in these things? Well, we have hydrogen bonding. So therefore, if we just compare methanol, boiling point of 65, not to methane, but to ethane, because ethane has got a similar molar mass to methanol. If you add it up for methanol, you've got, let's see, 32. Ethane has a molar mass of 30, right? Ethanol closer to propane in terms of molar mass, propan-1-ol closer, or propanol generally closer to butane, and so on and so on and so on. And you can compare that the boiling points of the alcohols much higher than the equivalent molar mass alkane there because of the presence of hydrogen bonding. If we plot them out, we do see that they start to get closer to each other. Here's the alcohols, right? Very much bigger boiling points compared to the alkanes here in red, but as the number of carbon atoms increases, they get closer together. And of course, the reason for that, as we discussed last week, is that as you go through making these molecules bigger and bigger and bigger, the hydrogen bonding decreases, the importance of London dispersion increases, because the longer the chain, the smaller the part of the molecule that the OH group represents. We see this not just with those trends in boiling points, but also trends in solubility. The first four alcohols on my list here, so carbon 1, carbon 2 and 3 carbons, completely miscible with water, in other words soluble in all proportions, but that solubility decreases significantly with 4 carbons, 5 carbons, and pretty much negligible when you get down to 6 carbons. Conversely, remembering of course like dissolves like, as we get more and more of the carbon chain in there, so more and more London dispersion, the more soluble these become in hexane. In indeed methanol hardly soluble in hexane at all, which just has London dispersion. All the other ones miscible, in other words soluble in any ratio. So there we see a lovely illustration, expansion upon points that we made last week, of the importance of considering the whole molecule, not just saying, oh look, it's got OH, it's got a hydrogen bond. Now let's shift attention to another oxygen containing type of molecule, carbonyl compounds. Here's our generic carbonyl compound. It has a polar bond in it, the slightly positive carbon, the very slightly negative, and when I say very slightly negative, I don't mean it's only a little bit negative, I mean it's quite a bit negative. Okay, so they've got dipole forces, and this is illustrated quite nicely, of course, in the boiling points. If we go butane, you can see these are pretty much the same because you've got London dispersion forces. Propanol has a very similar molar mass, identical molar mass to butane, very similar to butene, and notice that the boiling point is significantly higher than those two hydrocarbons. Acetone, again, same molar mass, teeny bit higher than propanol, but essentially the same boiling point there. For comparison, propanol boiling point much higher. And of course, if we think of these in terms of intermolecular forces, the hydrocarbons, London dispersion, the carbonyl compounds, dipole, and good old propanol has hydrogen bonding. However, the fun, extra fun thing with the carbonyl compounds is now we can use these as an illustration of kinda like dissolves kinda like. Because if we think about solubility in water, your hydrocarbons, negligible solubility. Propanol, though, 20 grams per 100 mils of water. Acetone is miscible. And the reason for that is that carbonyl compounds can't hydrogen bond with each other. When you have a pure carbonyl compound, it can only have dipole forces. But you start mixing it with, for example, water. Well, water can donate and accept hydrogen bonds. Here we have this oxygen can be a hydrogen bond acceptor. In other words, the water can come up with a slightly positive hydrogen, which can interact with a hydrogen bond with a slightly negative oxygen. There's no oxygen here for it to make a hydrogen bond, therefore it can't hydrogen bond with itself, but it can hydrogen bond quite happily with hydrogen bonding donors. So the carbonyl compounds, dipole forces, giving you an effect on the boiling point, and the fact that it's a hydrogen bonding acceptor, meaning that it's soluble in water, is significant. And indeed acetone, miscible, just like the one propanol, which has of course hydrogen bonding donor and acceptor capabilities. Talking of hydrogen bonding, donor and accepting capabilities, let's think about our carboxylic acids. So what carboxylic acid has a molar mass of 58, 56, 60? Well, of course, ethanoic acid. And look at that boiling point. All right, higher even than the 1-propanol because, of course, it has hydrogen bonding capabilities as well. But more than 1-propanol, when we look at a carboxylic acid, we have, in fact, 2 groups for hydrogen bonding in there. We've got the hydrogen bond acceptor, akin to the C double bond O we saw for the carbonyl compounds, but also the hydrogen bond donor and acceptor, akin to the alcohols. So that means that carboxylic acids can actually dimerize, in other words, 2 carboxylic acids hanging out together, forming effectively a double hydrogen bond with each other. Okay, and this dimerization really leads to an increase in that boiling point, even over that of the propanol. As far as miscibility goes, remember for the alcohol, these were miscible with water down to 3 carbons, while acids miscible with water down to 4 carbons. 5 carbons, pentanoic acid, reasonably soluble, but then you start really seeing the decrease in solubility, significant decrease in solubility in water, because of course, again, even though you got this super duper double hydrogen bond bit up the front, the longer the organic chain, the less soluble it's going to be in water. Finally now, let's discuss amines. Don't know how much you know about amines, but the functional group is of course a nitrogen in there. If we list out our nice little collection of molecules that illustrate London dispersion, dipole-dipole and hydrogen bonding, and then we think about some amines that have these same molar masses. There's the primary amine, because you've got it attached to 1 carbon. Propylamine, molar mass of 59. Its isomer, N-methyl ethylamine, so this is a secondary amine. You've got a methyl group and an ethyl group as part of the amine. And then finally, the tertiary amine, where you just got the nitrogen with the 3 methyl groups. So you would expect, would you not, for these two to have a nice high boiling point akin to, say, propanol, because you can do the hydrogen bonding. Indeed, some of you might even argue, look, we got 2 hydrogens there for the primary amines, maybe it's going to be even higher. And then I think you probably accept there's no hydrogen here for a hydrogen bond donor, but it can presumably act in the same way as our carbonyl compounds in terms of solubility, because it can act as a hydrogen bond acceptor. Now, something to bear in mind that doesn't often get pointed out, certainly at A level, is that not all hydrogen bonds are alike. Oxygen is much more electronegative than nitrogen, and so hydrogen bonds involving oxygen are much better than those involving nitrogen. And we can see this with these boiling points. There we are, the propylamine, the primary amine, still higher than if it was just London dispersion, but the boiling point akin to if you just had dipole-dipole, because yes, we've got hydrogen bonds here, but they're weaker than the oxygen containing hydrogen bonds. We mentioned this has got 2 versus the secondary amine only has 1. Does that have an effect? Absolutely. There's the boiling point of the secondary amine. And then, as we predicted, going down to the tertiary amine, only dipole-dipole, pretty low boiling point there overall. So somewhat shocking the first time I saw this, that the amines and physical properties not nearly as affected by the presence of hydrogen bonding as the alcohols. Solubility does still have a nice effect, and the first 5 carbon amines are all water miscible. As we pointed out, when you start throwing water around the place, now you have the capability of an amine acting as a hydrogen bond acceptor from the water, and now you've got that oxygen involved, so the hydrogen water, so hydrogen bond's a little bit better, and so we do see a significant effect on the solubility. Anyway, a little use of our organic chemistry studies to just augment what we talked about with intermolecular forces. Hope it was fun.